nurse that I had Friday said I was the first patient on this drug that didn't have a reaction during the thing, but mine was delayed, I think. Well, it wasn't as bad. This woman across the way, she had chest pains and all sorts of stuff, and that's normal. I didn't have any of those, but boy, it's wiped me slick. Okay. We're now recording. Let me get the announcement in. I know some of you may be participating, but in case you hadn't yet decided, this is from Ms. Gerasi. She's trying to build a strong math team for next year. Please, she's writing this to us, if we have students in Math 100, 112, 113, or Math 125 who will be here at Lawson in the fall, and they need calculus, she said come Friday, but now it's going to Monday afternoon, 3 o'clock?
It's actually both days.
Both days, okay. Friday afternoon at noon and Monday at 3? Okay. So go either day, both days, and if you want to meet here, maybe not today, but once I get the feeling better, anytime during my office hours, I'll be glad to run some practice things as well, and they're fun. It's a good deal. Okay, let's get started here with the slideshow from the current slide. And the first thing I want to know, any questions on anything we've covered so far? All right. Now, we've been kind of heading this way. This is sort of one of the next logical steps with our approaches toward calculus, and this is the properties of continuity. Now, up till now, we've been talking about limits and, whether the limits exist or not, left-hand limits, right-hand limits. This is going to tie some of this together. And one of the big theorems here is the properties of continuity. So let's start with, on the x-axis, b is any real number on the x-axis. And f and g are two functions that are both continuous at x equals c. So let me back up a bit. I thought we were going to say x equals b. C is on the x-axis, okay? B is any real number. F and g are continuous functions at some point x equals c, and they're continuous there, okay? Then the functions listed below are also continuous at c. Any scalar multiple of either of those two functions will also be continuous at c. Just multiplying a real number by a continuous function, it'll still be a continuous function. Sum or difference. The sum or difference of two continuous functions will be a continuous function. Okay? And the product of two continuous functions will be a continuous function. And with one little exception, the quotient of two continuous functions will be a continuous function as long as the g at set value c is not equal to 0. Here, f could be 0, f or g could be 0 anywhere, no problem, they can still be continuous. Here it can't because g is now in the denominator. So g at c cannot be equal to 0. That will then introduce that's not the best word, a non-continuity, okay, if you had g of c equals 0. All right. So this list here summarizes the functions we've studied so far that are continuous at every point in their domains. Okay? Now, notice here that it's a weasel word here. At every point in their domains. Because if it's a points in the domain, they're continuous. I mean, it's kind of a circular argument here. Because if they're defined in the domain, if they're not defined, then they're not in the domain, well, then they're not continuous there necessarily. But polynomial functions are continuous everywhere because their domains are all real numbers. all real numbers, always, polynomial functions. That's a sub n, and I hope y'all remember this from earlier. These are your coefficients. These are numbers. A's, the A's are numbers here. The subscripts here are just identifiers. This is the coefficient that goes with the x raised to the nth power. That a sub n here has no, it's just a number, that's all. N is just a counter. It's not that part of the problem. This n, the exponent, is part of the problem, big time part of the problem, because that's the power to which the exponent of the variable is raised. Okay. Remind me. Tyler, okay. I thought it was, but I didn't want to tell you wrong. Okay. And I'll apologize ahead. I'm kind of flaky today because I had infusions Thursday and Friday, and I'm not over them yet. So I actually slept in this morning an extra hour or so just because I felt so rotten. But we'll try to make it through today. So, polynomial functions, these are coefficients. The A's are just numbers, okay? The N here is just a counter. It just identifies which A goes with which exponent. That's all it's doing. This N up here, though, is the exponent. That's part of the problem, okay? So A sub n, x to the n, plus A sub n minus 1 times x to the n minus 1 power, plus, and you count down until you get A sub 1, x to the 1, a sub 0, x to the 0, which of course is 1, so you don't even list that. Polynomial functions are continuous everywhere. Their domains are all real numbers, everywhere. Now, rational functions, which are ratios of two polynomial functions, tricky thing here, their domains are everywhere where q of x is not equal to 0. So if you make that their domain, then they are continuous everywhere on their domain. But of course, they're not continuous where q of x is equal to 0, because that's not part of their domain. So it's a little weaselly there, but that's true. As long as q of x is not 0, they are continuous everywhere except where q of x is equal to 0. Cheston's here. All right, radical functions, okay? F of x is equal to nth root of x. Now, if n is an even number, of course, x can only be greater than or equal to 0. Only greater than or equal to 0. If n is an odd number, it's good everywhere, okay? So radical functions are, their domains are x is greater than or equal to 0 for all even n's, all real numbers for any odd n's. And then your trigonometric functions. Okay, and again, there's a little hidden thing here. Sines and cosines are continuous everywhere because those are nice, smooth, continuous functions everywhere. Tangent and secant are not continuous at the half pies, okay? Because that's where your x values are 0. And of course, because tangent is y over x, secant is 1 over x. So you cannot be defined wherever the x is 0. Cotangent and cosecant are not defined, that's not part of their domain, where the y's are 0. In other words, the whole number of pi's. So those are the functions we've talked about so far that are continuous at every point in their domains. The trouble is some of their domains are not defined for certain values. By combining this theorem, the previous theorem, with this list, you can conclude that a wide variety of elementary functions are continuous at every point on their domains. Okay? That's almost universal. Okay? The thing is, you just have to realize some of their domains have places where they're not continuous, okay? No, that's not quite right. Domains exclude places they're not continuous. That would be the better way to say it. Okay. And why is this not advancing? Okay. This is just trying to mess with me. Why is PowerPoint not working? Okay, let's try it now. There we go. Now, here's example 6, bottom half of page 79. By theorem 111, it follows that each of the functions below is continuous to every point in its domain. Okay? Now, why would this be continuous to every point in its domain? It's a sum of two continuous functions. That's a polynomial function. Very, very simple polynomial function. F of x equal x, or let's call it g of x equal x. Sine x is another continuous function, and any sum of two continuous functions will be a continuous function. And not only every point in its domain, at every point, because both of those functions are defined everywhere. Okay? Now this one, f of x is equal to 3 tangent x, that's one of those that its domain is limited. X cannot be any half pi, but as long as that's taken into account, it's continuous everywhere else. Okay? And f of x, and this is just a scalar multiple of a continuous function. Okay? In its domain. Not continuous everywhere, but continuous in its domain. This then is a quotient function, and as long as cosine x is not equal to 0, and where would that be? No, the cosine x is 0 at the half pi's. Okay? So this is continuous everywhere except where cosine is 0. That would be at the half pi's. The numerator, continuous everywhere, because that's a polynomial function. The denominator, continuous everywhere, but it can't be 0 at certain places, so therefore you have to exclude the values where cosine is equal to 0. And cosine is 0 at the half pi's. All right, let's see what they did. The theorem 112 here. Oh, wait. Okay. They sort of pulled a trick on me, okay? I thought these were the same functions. They're not. Sorry. This next theorem, which is a consequence of theorem 1.5, which was way back, allows you to determine the continuity of composite functions, okay? Now this one's pretty simple. F of x is equal to sine of 3x, okay? This is a composite function. The sine of the function 3x. The function 3x is continuous everywhere. It's a polynomial function. So therefore, the sine function is continuous everywhere. So therefore, this will be continuous everywhere. That's the continuity of a composite function. All right. Now the next one you have to be a little more careful with. Why? The square root. Okay? But what has to be true about what's inside a square root? Of any even root. Greater than or equal to 0. Well, guess what? This function in here, polynomial function, x squared plus 1, greater than or equal to 0 everywhere, because x squared is always greater than or equal to 1, as long as x is a real number. And then you add 1 to it, and that's got to be greater than or equal to 1. So again, this will be a composite function that is continuous everywhere in the domain of the innermost function, which is all real numbers. How about the third one there? Again. Second. composite function. It's a tangent of the reciprocal function. So it is a composite function, but I think I know what you're trying to say. It's not continuous everywhere. It is continuous everywhere in the domain of the functions, because 1 over x, reciprocal function, its domain is all real numbers not equal to 0. Continuous everywhere there, and then tangent will then be continuous there, but it can't be at x equals 0 because that's not in the domain of that. So, I don't know, it's just a little, it will never be continuous at x equals 0. Ever. Okay, you can't do it. So here's theorem 112. Usually they give the theorem first and then give the examples. This one we gave the example first. Continuity of a composite function. If g of x is continuous, that's the innermost function here, okay, at some value x equals c, okay, and this will be at all real numbers c, this will be at all real numbers c, that one would be at all real numbers other than x equals 0. C cannot equal 0 on the third one, okay? So if f is, okay, if g is continuous at c, f is continuous at g of c, okay? And again, for any place that you put here, sine's continuous everywhere, square root's continuous everywhere as long as the argument is greater than or equal to 0, which it is, and tangent is continuous everywhere. Oh, wait. Forgot that one. I misstated that one. Certainly x cannot be 0, okay? But also x cannot be 1 over a half pi, okay? Because if it was 1 over a half pi, then that would be tangent of the half pi's, and they're not continuous there. So not only can x not be 0, but x can't be 1 over a half pi, any of the half pi's. So yeah, there is another value there. I sort of skipped over that. So then the composite function is given by f of g. Y'all remember this notation, right? F circle g. That's f. I call it f of g of x. Okay, and that's how you define it. That's contiguous to C. Okay. Good deal. Sorry. So let's describe the intervals. This is example 6. By the way, they do have some little proofs here, and the slideshow doesn't spend a lot of time on them, so I'm not going to spend a lot of time on them. However, if you are a math major, I can't remember, are any of you math majors? No, you're either pre-engineering or math or education or something like that. So you probably are not going to get that deep into proving. Math majors will do a little bit more. Remember that meeting I was telling you about? Goodness, a couple of those talks, they were talking about topology, surfaces, things that were so abstract, I saw no purpose for them whatsoever. There's got to be a purpose somewhere out there, but, those kinds of things you don't need proofs in. But if you're not majoring in that, you could probably get by without it. All right, so let's describe the intervals on which each of these functions is continuous. Where is f of x equal tangent x continuous? Help me.
Not in the half pies.
Okay, the half pies, usually we'll call that 2n plus 1 over, or times pi. Okay. Wait, sorry. My brain isn't working well today. Pi over 2n plus 1. Okay. Where n is any real number. If n is 0, that's going to be, no, I said it wrong again. Goodness gracious, the brain's not working. Goodness gracious. pi halves, half pi plus n pi. Goodness gracious. Okay. So any n being an integer, 0, that would be pi halves. 1, that would be 3 halves pi. -1 would be negative pi halves, okay? So any half pi, that would be where this function would be continuous, okay? Now, the b1, I'm sorry, function g. Where is that going to be continuous? All right, here's Elijah. Gracious. I hope I'm going to make it today. Obviously, here x cannot equal 0, right? Now, as x gets close to 0, this number gets bigger and bigger and bigger and bigger and bigger. Okay, right? Either big negative if it's coming from the left, or big positive if it's coming from the right. Okay? But the function just goes like this. The closer it gets to 0, the faster it goes up and down. Okay? But that's not defined for x equals 0. That's for every x not equal to 0. And at x equals 0, we're just going to define it at 0. So will that work? I still don't think it will, okay? Because the sine x is just going back and forth between plus or minus 1 on both sides, and just defining it x equals 0 is not going to make it continuous, okay? How about this one? That is one of those sort of strange ones, okay? Because here, as x gets close to 0, this part is going to 0. This part is going crazy between plus or minus 1. Well, 0 wins, okay? Because plus or minus 1 is not going infinitely large or anything like that. You may not know if that one would win. This one still isn't going to work, though, because no, it might. Let's see. Believe. Goodness gracious, I'm hot. Yeah. So again.
Can you explain like what that's saying, like in the bracket? You know how it has like this.
That what?
Like what that's saying right there, how it's got the equals and it's in the bracket.
Okay.
What is that?
Okay, yeah. You mean what this notation means?
Mm-hmm.
Okay. This is what they call piecewise defined function. Here's how you define this function g of x everywhere except x equals 0. And the x equals 0, we're going to define it slightly differently. Okay? Let's do another one. Let's say you go to pay your postage on an envelope. If the postage, what is it now? 40-something cents? Whatever. I'll just make up 48 cents. Okay? The postage is 48 cents for every x or weight less than 1 ounce. Greater than 1 ounce is going to be, say, 78 cents. And then greater than 2 ounces, so it's going to be, that's going to just define what the postage is at any point. So this is saying, here's what your function is anytime x is not equal to 0. Here's what it is when it is equal to 0. So piecewise defined function. This is not defined at x equals 0. You can't do it, period. But if you define it here, that does give a value for it. But that still doesn't make it continuous because it's going like this, and just because it's 0 here, it's still not going to be continuous. Okay. Now this one, on the other hand, this is a product of 0 times something that's going between plus or minus 1, and the 0 is going to, just because this is bouncing between plus or minus 1, multiply 0 by that, and you got it. Not defined at x equals 0, because you can't do that. But when you define it to be 0 there, that will work, or at least in my fuzzy thinking right now, it will. Yeah, they do that by the squeeze theorem, which we didn't really do a lot on. But let's see. I think they'll show the graph, so let's go on and show that. Okay, first one, the A one, the tangent function is undefined at all the half pi's. Okay, at all other points it is continuous. And here's the graph of that. Okay, at the half pi's, not defined, not defined, not defined, not defined. Now, I don't know if you realize or recognize this. I haven't seen this in other texts. They put big parentheses here, meaning everything up to minus, that would be 3/2 pi, but not counting 3/2 pi, and everything from minus 3/2 pi, but not counting it to here. So that's what these symbols here, those are big parentheses, meaning everything in between, but not the endpoints. So this is defined here and here and here and here. Everywhere on their domains, they're defined, it's just that their domains do not include the half pi's. Okay, so it's continuous on those open intervals from minus 3/2 pi to minus pi halves, from minus pi halves to pi halves, pi halves to 3/2 pi, in every interval. Pi thickness, almost pi thickness from your half, in between the half pi's. So it is continuous on each open interval in its domain. Okay? Not defined at the half pi's, but they're not in the domain. So that's how that one looks. Okay? You don't have to put any partial thing there. It's not necessary. In fact, you wouldn't be able to get anything that made it work there anyway. Okay? This one, y is equal to 1 over x, continuous everywhere except x equals 0. The sine function is continuous for all real values of x. It follows that it's continuous everywhere except x equals 0. Okay? Can you make it continuous there? No. Okay? Because the closer you get to 0, the faster these go up and down. That's all that happens from the left or the right. And they're doing like this, like crazy. And just because you define the x equals 0 at 0, it's still going up and down everywhere on either side of it, so it's never going to be continuous at x equals 0. Okay? So it's continuous on the interval from negative infinity to 0 and from 0 to positive infinity, but nothing in between. Even if you try to define a value at x equals 0, still not going to happen. Okay? So if you had just left it like this would have been the domain. Even putting here or 17 or anything else there still doesn't give you a continuous function. So that was almost useless to do, but you could do it, but it's still not going to be continuous there. Now, the function, similar to the function in part B, except that the oscillations are damped by the factor x. As x gets close to 0, the function is getting less. Now, here was a good old squeeze theorem, okay? Because you had this x in here, for any x less than 0, okay, then it's a strange way to put it, but this would be minus the absolute value of x. That guarantees it's negative. And this is, this function here is also less than or equal to, and this is always less than that, because you see sine 1 over x, as long as x is not 0, that's between plus or minus 1, okay? So this will be whatever value it is, times something between plus or minus 1, because sine is always between plus or minus 1. So this part over here is always less than or equal to this. This part over here is always greater than or equal to that. And because this, the absolute value function, this is it, this is minus absolute value of x, there's positive absolute value of x, then it squeezes down at x equals 0, even though it's not defined there. If you define that to be 0 there, sure enough, you have a continuous function there. So this one, putting in this value x equals 0 here, identifying it there, that gives you continuity there because on either side, this is going to 0. Not define it x equals 0, but on either side it's going there. So define it to be 0 there, and you got it not. Okay? So h, which is the function, this one right here, is continuous in an entire real number line as shown in that. If you had not included this, you could not say that because this function wouldn't be defined there. But if you put in x equals 0, h is 0, h equals 0 at x equals 0, then that does make a continuous set. Otherwise, you'd have a whole other function there. Now, this is a part of the limit stuff that I guess is really important, okay? We will use something like this one time, and you need it for that. But most of the rest of the time, we're going to be dealing with things that aren't so esoteric here that, oh, okay, yeah, this one example, we do need to know that, okay? But this is just to complete your knowledge that you understand what's going on here. All right. Now we're moving top of page 81, intermediate value theorem. Okay? Another really important theorem. Okay? Continuity, important, intermediate value theorem. This theorem, 1.13, important theorem concerning the behavior of functions that are continuous on a closed interval. Okay? So remember, now we're talking about functions that are continuous on some closed interval. It can't be one of those that has a place where it's not continuous. You have to be continuous on this closed interval. And here's what it says. If f is continuous on some closed interval from a to b, here a, and it counts the value a, up to b, and it counts the value b, this function f is continuous everywhere on that function, on that part of the domain. Now, here's the other thing. F of a cannot equal f of b. They can't be the same values. They have to be different somehow. F of a can be less than f of b, greater than f of b. They just can't be the same. Now, those are the endpoints. K is any number between f of a and f of b. So let's say f of a was down here, f of b was up here. Remember, these are on the y-axis. K is some number in between. Not outside of them, in between those two. Remember, f of a and f of b can't be the same, so there's got to be some values in between. Now, then there is at least one number c somewhere between a and b on the x-axis, such that f of c is equal to k. Gotta be, because, let's see if they have a figure. I think they do. Not quite. Okay. Number one, f is continuous, meaning from a to b, f is continuous. No holes, no gaps, no breaks, right? So, if f of a is here, f of b is here, then if it's continuous going from here to there, for every value in between a and b, c in between a and b, there's some k in between f of a and f of b, it's got to touch it somewhere. Because you can't get from here to there without touching it. Got to be. That's what it's saying. F of c is equal to k. It may be at more than one c, but there's got to be at least one place c where that's going to be continuous. All right. So the intermediate value theorem tells you that at least one number c exists, but it does not provide a method for finding that c. You just know that somewhere between a and b, there's got to be a c that f of c is going to be equal to k. Okay? These theorems are called existence theorems. It proves that they exist, it just doesn't tell you how to find them. A proof of this theorem is based on the property of real numbers called completeness, that you can't get from here to there without crossing everything in between. that completely covers everything in between. The intermediate value theorem states that for a continuous function f, if x takes on all the values between a and b, okay, then f of x must take on all the values between f of a and f of b. F of a and f of b. If it is everything here, it's got to be everything there. In other words, there's no holes. There's no gaps. There's no places where they are discontinuous. Okay? That's the intermediate value theorem, works for continuous functions. As an example of the application of the intermediate value theorem, let's consider a person's height. Okay? A girl is 5 feet tall on her 13th birthday and 5 feet 2 inches tall on her 14th birthday. Okay? Now, somewhere in between her 13th birthday and her 14th birthday, she was every little fraction of a height in between those two. She didn't suddenly jump up and skip 5 feet 1 1/2. Okay? She couldn't. She had to go completely through that. Sort of a dumb example, but it's there. Then for any height h in between 5 feet and 5 feet 2, every height there must have been at least one day time t equals t, okay, when her height was exactly that h. If h is some value between 5 and 5 2. That seems reasonable because human growth is continuous. You don't just suddenly skip a height. She couldn't have skipped 5'1" anywhere, okay? May have only been an instant that she was 5'1", but she had to be 5'1" sometime. A person's height does not abruptly change from one value to another. It's a smooth, continuous extension. Make sense? Okay. The intermediate value theorem guarantees the existence of at least one number c on that closed interval a to b where the function has a value f of function k, okay, a value k. There may, of course, be more than one number c such that that's true. Now, this would not be in a person's height, okay? So don't think about this one. But if here's f of a up here, here's the value a here, value b here, closed interval, okay? F of a is up here, f of b is down here. For every value k in between f of a and f of b, now f of a is greater than f of b, okay? For every value k, there's going to be at least one place where if this is a continuous function, it takes on that value. Up here, there's only one place. Down here, there's 3 places. Down here, there's only one place, okay? But there's got to be at least one place where it takes on that value k. So here it would be a c right here. Here it would be a c right here. Here it could be c1, c2, or c3. All take on the value k. Okay? So you can have more than one, but you've got to have at least one. If it's a smooth, keep wanting to say smooth. It doesn't have to be smooth. It has to be continuous. A function that is not continuous does not necessarily exhibit the intermediate value property. Okay? Here is a function defined everywhere from a to b. Okay? F of a is up here, f of b is down here, just like we had before. But f of a is defined from a to some point, say, you didn't want to call it c, call it something else, d. Not defined here, but defined here. So it's defined everywhere, but you have a discontinuity here. If you have a discontinuity, intermediate value theorem does not hold. Down here, fine, no problem. Here, fine, there, fine. But in between here, not fine. Okay. Now, don't want to get too esoteric here, but this function could have done like this, and then like this, and it would have been defined everywhere, but it's not. It wouldn't have to be, just because it can be a discontinuous function, but still have fit the intermediate value theorem, but that's not what it says. If it's a continuous function, it has to fit intermediate value theorem. Okay. Make sense? Okay. So the intermediate value theorem often can be used to locate zeros of a function that is continuous on some closed interval. And whether you remember it or not, you did this back in Math 112. Okay? You use the intermediate value theorem there. Because if you had an f of A was positive and a f of B was negative, you knew there had to be at least one zero in between if that was a continuous function. So that's one place that we use it. Specifically, if f of x is continuous on some interval A to B, f of A and f of B are different in sign. Okay? One's positive, one's negative. Doesn't matter which way it is. Then the intermediate value theorem guarantees existence of at least one zero. You may have 7 zeros in between there, but it's got to be at least one, because between these two, it's got to cross, if it's a continuous function, it's got to cross that x equals 0, or y is equal to 0 at least once. Okay, so that's where we're going to use it a fair amount. So here's example 8, and this is, goodness, I'm running out of steam fast. Top of page 82. Use the intermediate value theorem to show that the polynomial function f of x is equal to x cubed plus 2x minus 1 has a 0 in the interval from 0 to 1. How can you show it has one? All you're showing is existence. You aren't finding what it is, but how can you show that it does have a 0 in between 0 and 1?
Make x equal to 0?
Yeah, let's put x equals 0. And when x equals 0, what would that be?
0.
Plus
0.
Minus 1. So f of 0 is minus 1. Okay? Let's pick x equal 1. What would this be? Plus 2 would be 3. Minus 1 is 2. Minus 1 here. 2 here. Gotta have a 0 in between. At least 1. May have more than 1. It's gotta have 1. Why? What kind of function is this? Polynomial functions. They're smooth and continuous everywhere. So since it's a continuous function, f of 0 is negative, f of 1 is positive. There's got to be at least one 0 in between on the interval from 0 to 1. Perfect. That didn't tell you where it was. It just showed you there was one, an existence theorem. Okay. Let's see how it is. Note the f is a continuous function on that closed interval. In fact, it's a continuous function everywhere. All real numbers, that's a continuous function. Okay, specifically between 0 and 1. And the f of 0 is negative 1. F of 1 is 2. Follows that, since f of 0 is less than 0, f of 1 is greater than 0. There's got to be some point in between 0 and 1 where it's got to be exactly, precisely 0. Maybe more than 1, but there's got to be at least 1, because it's a continuous function on a closed interval. Okay. And we see here there is one and only one. Okay? You can therefore apply the intermediate value theorem and conclude there must be some value such that that's true. Okay? And here's f of negative 1. F of 0 is negative 1. F of 1 is 2. And this shows it doesn't do like this. It just cuts it once. It doesn't tell you what that value is. And don't even, you can start guessing at what the values are, but that's not what this theorem is telling you. It just says it does have a 0. Okay? And don't think it's going to be 0.5 or something else so common. It's probably going to be a fairly complicated number, I'll put it that way. In fact, they say here the bisection method for approximating the real zeros of a continuous function is similar to the method used back in, this example 8 one we just did. If you know a 0 exists on the closed interval from A to B, 0 to 1, then the 0 must lie somewhere in between that. So why not take a middle value, like 0.5? What you do, you then do alpha 0.5. Okay, that was exactly halfway between 1 and 0. Okay, that's what this is saying. See what value that is. Okay? Now, let's just do it. Let's go back to that. And let's do f of 0.5. Okay? Here's your function. So 0.5 cubed would be 0.125, right? Okay? Plus 1, twice 0.5, minus 1, so this will be 0.125. Now, I'm not thinking well today, so I may mess that up. So here at 0.5, it's slightly positive. Well, we know at 0 it's not positive. At 0.5 it is positive. So pick something in between those two. Now my next guess would have been f of 0.4. Why not? I mean, I'm not going to do the bisection because it looks like it's going to be closer to 0.4 than it is to 0.25. So let's do that. And that would be 0.064. No, wait. I'm not thinking well today. 0.16. Yeah, 0.064, wouldn't it? Okay. Yeah. Plus 0.8 minus 1. Okay. Well, this would add to 0.144 minus 1. So you see, now we've got a negative value. So at 0.4 it would be negative. So that'll go somewhere in between those two. And you keep zooming in on it, from either side and pick a value in between 0.5 and 0.4, like 0.45, And keep doing that. And after a while, you'll get fairly close to the answer. You probably won't get exact, because my guess is that's going to be a cube root of something, and most cube roots are not rational numbers. So you can get close, but not exactly get there. Okay. Now, your calculators will do this for you if you know how to use them. So by repeatedly bisecting the interval, you can close in on the 0 of the function. Okay? You will never probably get exactly there because all you're dealing with is rational numbers. It's probably going to be an irrational number. Now, hopefully before this term is over, I'll show you a much easier way to do it than the bisection method. Who came up with calculus? Does anyone remember? Isaac Newton. Also Leibniz did it too, but we usually think in terms of Newton. Not only did Newton develop calculus, he came up with applications of calculus that were way beyond. I mean, you would think just developing it would be enough. He came up, and there's a method called Newton's method that zooms in like crazy on the zeros of a function. And that's what your calculators do when you're entering that on your graphing calculators, and they come up with a value. It's you doing Newton's method. And it's really, really quick. This method, bisection method, takes a while. Okay. All right, that finishes 1.4. Homework exercises here. Do any of the odds, 5 through 9. All 3 of those are at calcchat.com. Number 5 is at calcview.com. Do any of the odds 11 through 29. All of those are at calcchat.com. 11's at calcview.com. Do either 31 or 33. Both of them are at calcchat. 31's at calcview. Do either 35 or 37 or both. Both of them are at calcchat. 35's at calcview. Do any of the odds 39 to 57. All of those are at calcchat. 47's at calcview. Do any of the odds 59 to 63. All those are at calcchat. 61 is a calc view. Any of the odds 65 to 69, all are at calc check. 67 is a calc view. Either 71 or 73, they're both at calc chat. Neither one of those are at calc view. Any of the odds 75 to 81, they're all at calc chat. None of them are at calc view. 81, 83 or 85, they're both at calc chat, but not at calc view. And do 87. Only one like it, that's at calc chat, but not at calc view. Any of the odds 81 to 93, they're all at calc chat, not at calc view. Any of the odds 95 to 99, all at calc chat, 95 is at calc view. And then, exploring the concepts, you don't have to do these, but not a bad thing to think through, 101 and or 103. I don't know, excuse me, if these are at calc chat or not. Usually they are, but because these aren't actually calculation problems, they may not be. The true false, again, I can't say for sure, but 105 to 109, hopefully they're at calc chat. I haven't looked it up to see. 113, not a bad one to look at. Let me just say, any of the odds 113 through, 127. And these are a little more complicated, okay? So don't get too wrapped up in these. If you are running into difficulties with them, you're not going to have anything this complicated on a test, but it may not be a bad thing to look at. Now, remember that paper that all of you are working on diligently, right? Okay, good deal. Justin just came in. Especially when you get into some of these higher level examples. Here was the Dirichlet formula, number 118. I think we talked about that in class. That is a potential paper topic. We already talked about that. There is also the Sigmund function, okay? And there's another possibility. Dirichlet, obviously, proposed by a guy named Dirichlet, or Dirichlet. If he was French, it would be Dirichlet, but he was German, so I think it's Dirichlet. But the Sigmund function wasn't named after a guy named Sigmund. It was a function that does something. So who developed it, or how was it developed? What is it used for? That kind of stuff would be another potential paper topic. You don't have to do that, but these just give you those. Now, this book is big on this Putnam exam challenge. And obviously there's this Putnam prize that they do, and they come up with really complicated type problems. If you want to take a look at that, you certainly can. I wouldn't get too wrapped up in it unless you just find that stimulating. Okay, I'll put it that way. All right, let me do this. Okay. Man. All right. Let's go to 1.5. Now, these sections in every trig book, calculus book I teach, I really have problems with them because the title of it is Infinite Limits. Well, number one, if it's infinite, it doesn't have a limit. Okay, so that almost seems like it's a contradiction in terms. Okay, now there are some circumstances when you can be approaching infinity and something could have a limit. But if you're approaching infinity, it doesn't have a limit. So it's almost contradictory, but I know what they're talking about, so let's hit it, but let's not get too tied up with it. Okay. The objectives here: determine infinite limits from the left and from the right, and find and sketch the vertical asymptotes of the graph of a function. These can be important, okay? So I don't want to belittle them too much, but just the title is the thing that bothers me: infinite limits. If it's got a limit, it's not infinite, okay? So consider the function f of x is equal to 3 over x minus 2. Okay? What kind of function is that? Something over something. Say again? A quotient, also called a rational function. Okay? Ratio of two entities. Okay? Now, where would you run into problems? If the denominator is 0, could that denominator ever be 0? X minus 2? Yes, it could. X equal 2 is going to be 0. So from the figure over here, we see that f decreases without bound as x approaches 2 from the left-hand side, because let's just call that, say, negative 1.9. Okay? I'm sorry, 1.9. Okay? Minus 2 would be negative 0.1, right? Okay? Well, that value would be 10, negative 10. You get closer to it, it goes even lower and lower. So it's not approaching the limit anywhere there as you approach 2 from the left-hand side. But approaching 2 from the right-hand side, say 2, this would be 2.1, that'll be 3 over 2.1, that would be, I forgot about my 3 there, but that would be 3 over 10, that would be 30, okay? 0.01 would be 300, okay? It's going increasing without bound as you approach there. Decreasing without bound as you approach from the left, increasing without bound as you approach from the right. Guess what, folks? No limit, okay? This is not going to have a limit. It decreases without bound as x approaches 2 from the left, increases without bound as x approaches 2 from the right, because that's a discontinuity. You cannot have 3 over 0. You cannot plug in a 2 there. Okay. So you see this is going up negative 30 here, negative 300 there, negative 3,000 there, 30 here, 300 there, 3,000 there. You know, going up very, very quickly. No limit as x approaches 2. Okay? Now, so, no limit. Why call them infinite limits? Okay, it just gripes me. You know, that's what all calculus books do. They call them infinite limits, which is contradictory to me. Okay, so this behavior is denoted here. The limit, which is crazy, it has no limit, as x approaches 2 from the left, is 3 over x minus 2, and that would be negative infinity. That is no limit. I would say no limit does not exist. And this one would be positive infinity. Okay? So the symbols infinity and negative infinity refer to positive infinite and negative infinite values. Okay? I don't know. It seems like to me if they say refers to positive infinity and negative infinity, why would they say one is infinite, one is infinity? I don't know. I think it's just a typo. These symbols do not represent real numbers. They aren't limits, okay? There are no numbers there. They just increase or decrease without bound. They're convenient symbols used to describe unbounded conditions more concisely, okay? So they're not really describing a number. They're just saying they increase or decrease without bound, which then why call them a limit? I don't know. The limit in which f of x increases or decreases without bound as x approaches c is called an infinite limit, which to me is contradictory, self-contradictory. So here's the definition of these infinite limits. Let f be a function that is defined as every real number on some open interval containing some value c, except possibly at c itself. The statement, the limit as x approaches c of that f of x is infinity, means it gets infinitely large. It doesn't have a limit. That means that for every value m greater than 0, capital M greater than 0, there exists some value delta greater than 0, such that anytime the f of x is greater than m, it's going to be greater than m whenever the x minus c is going to be within that delta. Delta is how close to cx is, okay? M is some value up here. No matter how big you get, you can always find a delta that's going to make it even bigger. Okay? In other words, the limit doesn't exist. Okay? Or as x approaches c, f of x as x approaches c going to negative infinity, that means there's some. Now, in some books they use a little m here, and that's when uses a capital N. There, that's less than 0. There exists some delta greater than 0, such that if you get within delta units of that x equals c, you can guarantee your f of x is still going to be less than that n. No matter how small that n is, you can always get even more negative than that. So to define the infinite limit, from the left, replace the absolute value of x minus c. Okay, this is just showing you how to prove it, I think. To define the infinite limit, which I hate those words. You can't define an infinite limit, okay? From the left, replace that 0 is less than absolute value of x minus c, less than delta, okay? In other words, you're somewhere within whatever delta you chose is 0. You're somewhere in between that. And do on this side c minus delta, okay, x in the middle, and c plus delta here. In other words, here's what you've done. You subtracted, boy, they're sort of sloppy here, I would say. Let me see if I can. It just looks like they just pulled something out of the air, or some not good, too great a body part here. Let's just say, let me get my pen activated again. I'm not sure I'm going to be able to do this the way my brain's working this morning. 0 less than absolute value x minus c less than delta. Okay. Now, remember an absolute value. Let's just assume that x is greater than c, okay? Then you can write this absolute value to be c minus x here would be less than x is less than x minus c. Okay, I think that's the way we're going to go. And if x is greater than c, this is going to be equal to your delta. Okay. So what we're going to do next is, I still don't see how they quite get there. Let's not beat the dead horse anymore. Let's just let it go. Okay, I think what they do is do it first from the left and from the right. they're leaving out an awful lot of steps here, and I just don't feel like going through them all here. If this was the positive value, then C minus X would be the negative value, okay? And this is the difference between C and delta. That's this thing right here. If that's less than your X and less than the C, okay, if you're in this area here, C minus X would be here. X is some value in between here. C minus X would be there. X would be somewhere in between there, and C would be here. So that's what it's saying here. And on this side, your C is less than X, if X is over here, and that's less than C plus delta. Okay. So that's what it's saying. You're either in this part or that part, is basically what they're saying. Okay. And I don't really see what the point of doing all this is, but what they're saying is if you're in that, this increases without bound. That M was the place where it's equal to delta here or equal to delta here, and anything inside that, you're going to be greater than M. And that increases without bound. So there is no limit. So why call it an infinite limit? Just say there is no limit, but they call it infinite limit. Okay. Sorry. Probably beat that to death. Let's do example 1 here. Determine the limit of each of the functions shown in this figure as x approaches 1 from the left and from the right. Okay? So, obviously, x cannot equal 1, right? But as x is approaching 0 from the left-hand side, approaching 1 from the left-hand side, then this thing gets to be, and x is getting closer and closer to 1, this thing is getting smaller and smaller and smaller, and you're squaring it, that makes it a very small positive number. And 1 over that is going to be a very large positive number. But approaching it from the other side, from the right, x minus 1 is positive. Okay? But then you're squaring it, it stays positive. And the closer you get to x equal 1, the smaller this gets, and the bigger 1 over that. Okay? So that has an asymptote at x equal 1. Okay? Here they just threw in the term asymptote. We've had them before. That's where the value cannot take on, the function cannot take on that value, x equal 1. Because x minus 1 cannot equal 0, so x cannot equal 1. Over here is to the first power. As you approach x from the left-hand side, this becomes a negative number. Okay? X is approaching 1 from the left-hand side. X minus 1 is negative. That's negative, so negative over negative is positive. As you approach x from the right-hand side, x is greater than 1, so this is approaching 1, and that's going to be a positive value, but you're dividing it into a negative number, so that gets very negative. So this will be, again, a vertical asymptote to x equal 1. Here, both of your limits are going to positive infinity. Here, the left-hand limit is going to positive. The right-hand limit is going to negative. Okay? But anytime you have an asymptote, one or the other is going to go to an infinity. Left or right, one's positive, one negative, both positive, both negative. Okay? All right, I don't know what else they wanted you to do with that, but that is what's happening here. So when x approaches 1 from the left or right, x minus 1 squared is a very, very small but positive number because it's squared, okay? And when you do 1 over that, it becomes an extraordinarily large positive number, okay? So it's approaching positive infinity from left or right. So this, and again, this is, to me, kind of crazy nomenclature. It doesn't have a limit, but it from both sides, positive or negative, is going to a positive infinity. Okay, limit from each side. Doesn't have a limit, but they're going to positive infinity. Okay, and that shows that. Whereas when x approaches 1 from the left-hand side, x minus 1 is a very small negative number, but a negative divided by a very small negative is going to be a very large positive number, so it's approaching positive infinity from the left, negative infinity from the right. Okay? Positive infinity from the left. When it approaches 1 from the right-hand side, that's a very small positive number, and then when you divide that into negative 1, you would get a very large negative number. So it approaches negative infinity from the right. Okay, so you can conclude this. And again, it doesn't have a limit. Okay, it's going to negative infinity, but they call it a limit. I don't know. It just bugs me they use that terminology, but they all do. So you have to live with it. Okay. Any questions on that? Okay. Before you get the vertical asymptotes, they do have a little technology blurb at the bottom of page 88. And basically it's what it's telling you is if you're trying to do this on a graphing calculator or some type of tabular thing, if you happen to get one of those values, it's going to give you an error. If you don't happen to hit right on that value, you're going to get very large negative or positive or both, values, but it'll give you an error there. So that means it's going to an infinity, basically. So let's now talk about vertical asymptotes. I think you've already hit these, and you've already sort of talked about them. Sorry. If it were possible to extend the graphs that we were just doing, okay, toward positive and negative infinity, you would see that each graph becomes arbitrarily close to some vertical line, x equal 1. That was the value for which the domain was not defined. You cannot have x equal 1 here because the denominator can't be 0. You can't have x equal 1 here because the denominator would be 0. Those are called your vertical asymptotes, and these lines get closer and closer to that, but will never, ever, ever touch it. They get closer, closer, arbitrarily close. They look like they're going to touch. They never will. Okay? Or this one will be going this way, this one that way. They cannot touch or cross. That's what makes a vertical asymptote. Okay? It's the place where your denominator cannot equal 0. Okay? That's going to be your vertical asymptote. You did this back in 112 in rational functions, hopefully. Okay? So here's the definition of vertical asymptote. If f of x approaches infinity, or negative infinity, as x approaches some value c from the right or from the left, then the line x equals c is called a vertical asymptote of the graph of f. Now, in example 1, note that each of the functions is a quotient and that the vertical asymptote occurs at the number for which the denominator would be 0. Okay? The numerator can't be 0. Why? What if the numerator was 0 and the denominator 0? Indeterminate form. Yeah, you can't say that it doesn't exist there. It may not exist, but it may not have a vertical asymptote there. The next theorem generalizes that observation. Okay? Now, time out. These functions we're talking about, the quotient functions, these have to be reduced quotient functions. In other words, if you had an x squared minus 1 in the numerator and an x minus 1 in the denominator, you could reduce that. That wouldn't have a vertical asymptote but x equal 1. Okay? But x plus 1 in the numerator and x minus 1 in the denominator would have one. X squared minus 1 would have one. Okay, so here is the next theorem. Vertical asymptote. I'm just a about out of G's. Let's let f and g be continuous functions on some open interval containing some value c, x equals c. Now, if f of c is not equal to 0 and g of c is equal to 0, now your f is going to be in the numerator, it's not 0, g of c in the denominator, and it could be 0, then there exists an open interval containing c such that g of x is not equal to 0. Okay? So you can have an open interval containing c somewhere in between. You have values in between here where that g of x is not equal to 0, but x equals c, it is equal to 0. For all c not equal to 0 on that interval. Then the graph of the function h of x, and we'll call this the rational function, f of x over t of x, will have a vertical asymptote to x equals c. If that f of x could have been valued 0, you can't say this. But if this is not equal to 0, and this can be 0, is 0, x equals c, then you will guarantee to have a vertical asymptote there, and you're going to have basically what they call infinite limits. In other words, no limits. Okay, limits going to infinity. So here's example 2, bottom of page 89. Now, I think I've said this before, but let me say it again. A few of these examples, not all of them, but a few of them will have these little red lines under them that says see larsoncalculus.com for an interactive version of this type of example. So you have calcchat.com for your odd number exercises, calcview.com for selected odd number exercises, and you have larsoncalculus.com for some of these selected examples. Okay? So, here is your example. Here's your function, h of x is equal to 1 over 2 times x plus 1. Okay? Is that numerator ever 0?
Yes.
Never. It's 1. It can't be 0. Okay. Is the denominator ever 0?
Yes.
Where?
-1.
X equals -1. You're guaranteed you have a vertical asymptote at x equals -1. No doubt about it. When x is equal to -1, that denominator is 0, the numerator is not 0, you're guaranteed to have a vertical asymptote there. Will you have a limit there? No, you won't. They will call it an infinite limit, but basically it means you have no limit. As x approaches -1 from the left, then that would be, say, -1.1 plus 1, that would be a negative number. This is going to negative infinity as it approaches -1 from the right-hand side. The x is greater than 1, so that's going to be positive. That will be going to positive infinity. Okay? So these have what they call your infinite limits. I want to say no limit there. Okay. So by theorem 114, you can conclude that x equals -1. There is a vertical asymptote, and it's going to negative infinity when you approach -1 from the left, positive infinity as you approach from the right. Okay. Vertical asymptote. It has no limit at x equals -1. I wish they'd just say that. They talk about positive and negative infinite limits. Okay. Now, how about this one? H of x is a rational function. X squared plus 1 in the numerator, x squared minus 1 in the denominator. What can you tell me about it? Is that numerator ever 0? Never! Because x squared is always going to be greater than or equal to 0. Add 1 to it, it's going to be greater than 0. Can't ever be 0. How about the denominator?
Yes.
Yes, x equals 1 is going to be 0. X equals minus 1 is going to be two vertical asymptotes. One x equals -1, one x equals 1. Okay? Now, what can you tell me about those? When x is to the left of -1, then this is going to be a negative number here. Okay? That's always going to be positive. That's going to be a negative number. Okay? Because x is to the left of -1. So, say -2. That would be, so this is going to be negative. That's going to be negative. Negative times negative is positive. That's positive. So that's going to be some positive value going to positive infinity as x approaches. Okay, I started off saying negative. Okay. Let's back off a minute. -1, yeah. So positive going there. In between -1 and 1, this is going to be negative, right? This is going to be positive, okay? So this will be negative, that's positive, so in between, this is going to negative infinity. Beyond x equals 1, that's positive, that's positive, that's positive, everything's positive, that's going to positive infinity. So we have a pretty good idea, if my brain's working right, how this is going to look, and there it does. Okay? As x is approaching -1 from the left, that's going to positive infinity. +1 from the right, it goes to positive infinity. -1 or +1 from anywhere in between, then is going to negative. Okay? So that's how this one looks. Okay. Now, couple of other things that this is just a refresher on what you had back in 112. Okay? Does this have a x-intercept? That would be where y is equal to 0. Y would be your h of x. Is that ever equal to 0? No, the numerator would have to be 0. It's always positive. So no x-intercept. Does it have a y-intercept? Sure, that's for x is equal to 0. And that would be at -1, and there it is. Right? Okay. Now, we talked about vertical asymptotes. That's anywhere that the denominator would be 0, and that would be a +1 or -1. Okay? Vertical asymptote with +1 and -1. This also has a horizontal asymptote, and that's for your ratio of the leading terms. What is that? X squared over x squared is 1. So y is equal to 1. There is your horizontal asymptote. That's not what we're talking about here, but just a little bit of a refresher from back when you had this in Math 112. Okay. Now, this is the B part of example, no. I'm sorry, okay, sorry. The A part was that one, the B part was this one. Here's the C part of example 2. Sorry, I got kind of lost here. Here we have h of x is equal to cotangent x. What is cotangent? You can see here. Ratio identity, quotient identity, cotangent is cosine over sine, tangent is sine over cosine, cotangent is cosine over sine. Now, is that denominator ever equal to 0? Where is sine equals 0?
You got confused earlier. So
Second?
I got confused earlier. So it would be at the half size.
It's at the pi's, at the whole number of pi's, not the half pi's. Cosine is 0 at the half pi, sine is 0 at the whole pi's. If you think about it, sine starts at 0 and then 0 pi, 2 pi, 3 pi. Okay. So this is the whole pies. Now, cosine is also 0, but never at the same place. So you'll never have a 0 over 0, okay? When this one's 0, that one's not. When this one's 0, that one's not. So you'll never have a 0 over 0 or an indeterminate form, but you can have vertical asymptotes. And where are these? That's everywhere that x is in whole pi, okay? Which would be at 0, at pi, at 2 pi, 3 pi, negative pi, negative 2 pi, negative 3 pi. These are all your vertical asymptotes for cotangent x, okay? So the vertical asymptotes occur there because you can have cosine x being 0, but never at the same place as sine x is equal to 0. So that's what will produce that. And this looks a lot like your tangent function, except tangent function has the zeros at the whole pies because it's sine over cosine, and has its asymptotes at the half pies because of the cosine. This one has the zeros at the half pies, right there, there, but has the vertical asymptotes at the whole pies. The other thing about it is tangents are always increasing functions, cotangents are always decreasing. Just the nature of the beast. Because cosine starts at 1 when x is equal to 0, and this is 0 there, so that's positive infinity. And then it goes, and at the quarter pies, this is 1, right there, okay? Positive 1. And then when you get down to this being 0 at the half pi, that is 1, you're here, and then it goes negative. So it's a decreasing function, whereas tangent is increasing. Way more than what they wanted you to do in this problem. Okay. So by the graph of that function, infinitely many vertical asymptotes, they occur at your n pies, your whole number of pies, where n is any integer. Okay. I think we're going to have to stop there because I believe we just ran out of time. So we will start next time. Whoa. They skipped example 3 and 4. So we'll start next time at example 3 on page 90. Then we'll get to this theorem. And then we'll go on from there. Let me give you a few homework exercises here. Do either 3 or 5. They're both at calcchat.com. 3 is at calcview. Either 7 or 9. They're both at calcchat. 7's at calcview. Do any of the odds 11 through 15. Those are all at calcchat. None of them at calcview. Any of the odds 17 to 31. They're all at calcchat. Number 25 is at calcview. And we'll stop there and pick up the rest of those later. Okay? Good deal. Thanks for putting up with me today. Sorry I was sort of out of it. Hopefully I'll be feeling better on Wednesday. But who knows?